In 2017, astronomers detected an unusual object zipping through our solar system at high speed. Designated Oumuamua, Hawaiian for Scout or First Distant Messenger, it was the first confirmed interstellar visitor ever observed. Unlike typical asteroids or comets bound to our Sun, Oumuamua's trajectory was hyperbolic. It was moving too fast to be gravitationally bound, indicating it had come from beyond our solar system. This interstellar origin alone was remarkable, but what truly set Oumuamua apart were its bizarre characteristics and behavior. Its discovery sparked intense scientific debate, with some researchers raising the extraordinary suggestion that Oumuamua might be alien technology due to its unexplained acceleration and other anomalies. In this report, we explore what we know, and don't know, about Oumuamua, the theories surrounding its nature, and plans to investigate future interstellar objects. Oumuamua was first spotted on October 19, 2017, by the Pan-STARRS 1 telescope on Haleakala, Hawaii. Initially classified as a comet, C/2017 U1, it was later reclassified as an asteroid, A/2017 U1, when no coma or tail was observed. Ultimately, astronomers determined it warranted a new classification, the first interstellar object, hence 1I/2017 U1. At the time of discovery, it was already on its way out of the solar system, having passed its closest approach to the Sun on September 9, 2017. Its inbound trajectory traced back to the general direction of the star Vega in the constellation Lyra, though it did not originate from Vega itself. By the time we noticed it, Oumuamua was about 33 million kilometers from Earth and fading fast. Within 2 months it had become too dim to study with even the largest telescopes, escaping our grasp. Limited observations revealed that Oumuamua is small. Estimates suggest it could be as large as 1,000 meters long, but possibly as small as 100 meters. Its brightness varied dramatically every few hours, indicating it was tumbling end over end with a rotation period of roughly 7.3 hours. The pattern of brightness fluctuations implied an extreme elongated shape, perhaps 5 to 10 times longer than it is wide. Scientists envisioned it as either a long, cigar shape or a flat, pancake shape, since such an irregular object would reflect sunlight unevenly as it tumbles. This unusual morphology was one of the first hints that Oumuamua was no ordinary asteroid. For comparison, most asteroids and comets are roughly rounded or slightly elongated. An interstellar object of such extreme proportions had never been seen before. Another oddity was that Oumuamua lacked any visible coma or tail. Even as it passed relatively close to the Sun. Typically, a comet would release gas and dust when heated, forming a fuzzy coma and tail. Yet observations with multiple telescopes, including the Spitzer Space Telescope, detected no infrared emission from Oumuamua, suggesting no surrounding cloud of warm dust. Spitzer's null detection also indicated that if Oumuamua had a comet-like tail, it was at least 10 times fainter than the smallest tail Spitzer could have seen on a similar comet. In other words, Oumuamua appeared to be unusually dark and/or small, and if it was outgassing, it was doing so without producing much dust. Its reflectivity, albedo, was estimated to be very low, possibly only a few percent, meaning it absorbed most of the sunlight it received. This aligns with it being an inert rocky or metallic object rather than a typical comet. However, the absence of a coma made it difficult to reconcile with known solar system asteroids as well. By reconstructing its orbit, astronomers found that Oumuamua entered our solar system from interstellar space, traveling at an initial speed of about 26 km per second relative to the Sun. As it swung around the Sun, its speed climbed to nearly 87 km per second at closest approach, perihelion. After rounding the Sun, it should have gradually slowed down under the Sun's gravity, following a predictable hyperbolic path. Instead, as it departed, astronomers noticed a tiny but significant deviation. Oumuamua was accelerating away faster than expected. This subtle acceleration, amounting to only a few millimeters per second squared, was enough to cause a measurable change in its trajectory over time. In physics terms, an object will accelerate only if a force is acting on it. For a comet, the usual explanation is outgassing. As sunlight heats the comet, sublimating ice into gas, the expelled gas provides a gentle thrust, like a mini rocket engine, that can alter the comet's path. But in Oumuamua's case, there was no visible outgassing to produce such a push. This was perplexing. Here was an object behaving like a comet, with unexpected acceleration, yet looking like an asteroid, no tail or coma. It was, as one scientist put it, a comet in disguise. Anomalous acceleration and scientific debate. The discovery of Oumuamua's anomalous acceleration ignited a firestorm of hypotheses to explain it. Scientists scrambled to find a natural explanation for the extra push, while others, more controversially, floated the idea of an artificial origin. Let's examine the leading theories. Outgassing from a dark comet. The most widely favored explanation among astronomers is that Oumuamua is an interstellar comet that did outgas, but in a way that we couldn't easily observe. A team led by Darrell Seligman and Jennifer Bergner proposed that Oumuamua might be composed largely of water ice with pockets of trapped hydrogen gas. In the frigid environment of interstellar space, cosmic radiation can convert some water ice into hydrogen gas, which becomes trapped within the ice. When Oumuamua approached the Sun, the warming ice could have released this hydrogen gas. Unlike water vapor or dust, hydrogen gas is invisible to telescopes. If enough hydrogen vented from Oumuamua, it could provide the observed acceleration without producing a visible tail. In this model, Oumuamua is essentially a dark comet, a comet whose outgassing is dominated by invisible gases, leaving it looking like an asteroid. This theory could explain both the acceleration and the lack of a detectable coma. Seligman and Bergner's calculations showed that such hydrogen outgassing from a water ice-rich object could indeed match Oumuamua's trajectory. It's worth noting that this idea was bolstered by laboratory experiments demonstrating that ice exposed to radiation can trap and later release hydrogen. While this hypothesis is not proven, it is considered plausible by many scientists as a natural explanation. Light sail, artificial origin. A far more speculative theory, put forth by Harvard astronomer Avi Loeb, is that Oumuamua's acceleration was due to radiation pressure from sunlight pushing on an extremely thin, large object, essentially acting like a solar sail. For this to work, Oumuamua would need to be an extraordinarily flat and lightweight structure. Loeb calculated that if Oumuamua were a thin sheet only a millimeter or so thick and perhaps 100 meters to 1,000 meters across, the pressure of sunlight alone could produce the observed acceleration. Such an object would reflect sunlight efficiently, potentially explaining its bright flashes and also why it appeared point-like. No tail, a thin sail would not produce dust. The catch is that no known natural process would form a millimeter-thin interstellar object of that size. Loeb argued that this implies Oumuamua might be artificial, perhaps a derelict solar sail or probe from an alien civilization. This idea garnered significant media attention but is viewed with skepticism by most of the scientific community. Critics point out that an alien solar sail is an extraordinary claim requiring extraordinary evidence, and so far we have no direct evidence of artificial origin. They argue that natural explanations, like the dark comet model, should be exhausted first. Loeb's hypothesis remains controversial and is not widely accepted, though it has spurred interesting discussions about how we might detect extraterrestrial technology in the future. Other hypotheses, a variety of other ideas have been suggested to explain Oumuamua's behavior. For example, some researchers considered if it might be a hydrogen iceberg, solid H2, since hydrogen ice would sublimate, turn to gas, very efficiently when heated and could push the object without a visible trace. However, it was quickly realized that interstellar space is too warm and H2 ice is too fragile. Any large hydrogen iceberg would likely evaporate long before reaching our solar system. Another thought was that Oumuamua could be a fragment of a Pluto-like planet from another star system, blasted off by a collision and sent our way. Such a fragment might be rich in volatile ices, like nitrogen or methane, that could outgas quietly. Yet another hypothesis proposed that Oumuamua's acceleration was due to tidal forces from the Sun, but calculations showed this effect would be negligible. In the end, most scientists have converged on the outgassing of invisible gases, like hydrogen, as the most plausible natural mechanism, while acknowledging that the case is not closed. It's important to emphasize that no consensus exists on what Oumuamua was. The object's brief visit left us with more questions than answers. The limited data mean we cannot definitively determine its composition or origin. As astronomer Karen Meach, who led some of the follow-up observations, noted, "We saw something that we never expected to see, and so we have to stretch." Given the mysteries left by Oumuamua, astronomers are eager to catch the next interstellar interloper and study it in detail. The encounter with Oumuamua revealed a critical need. We were taken by surprise and did not have a dedicated mission ready to intercept or closely observe it. This is spurring efforts to be better prepared for the next visitor. Here are some of the key initiatives and plans in the works. Next-generation telescopes, new sky surveys will dramatically improve our ability to spot interstellar objects early. The most anticipated is the Vera C. Rubin Observatory, formerly LSST, in Chile, slated to begin its 10-year survey in 2025. Rubin's wide-field camera will scan the entire sky frequently, enabling it to detect faint, fast-moving objects like Oumuamua. Simulations suggest Rubin could find several interstellar objects per year, a huge leap from the one we've seen so far. Importantly, Rubin might catch such objects months in advance of their closest approach, giving us time to react. For example, whereas Oumuamua was only observed 40 days after its solar closest approach, Rubin could potentially flag a similar object 3 months before its closest approach, allowing astronomers to point other instruments, and possibly launch a mission, in time. This early warning is crucial for not missing out on valuable science. ESA's Comet Interceptor, the European Space Agency, is launching a mission called Comet Interceptor around 2029. This mission is unique. It will not target a specific known object, but instead wait in space for an opportunity. After launch, Comet Interceptor will enter a stable orbit, a parking orbit around the Sun-Earth L2 point, and remain there for up to 3 years, monitoring for any incoming comet or interstellar object. If a suitable target, especially an interstellar visitor, is detected with enough lead time, the spacecraft will fire its engines and perform a flyby to study the object at close range. The goal is to get high-resolution images and compositional data, essentially performing the kind of close-up flyby that we never got for Oumuamua. Comet Interceptor carries a suite of cameras and spectrometers to capture a 3D map of the object and analyze its composition. It's essentially an interstellar object ambulance on standby. While we can't predict when the next Oumuamua will appear, missions like this ensure we'll be ready to chase it down if it happens soon. There is a risk the mission might wait out its window without a suitable target, but scientists consider it a worthwhile gamble given the potential payoff. Project Lyra, interstellar probe chase inspired by Oumuamua. Researchers at the Initiative for Interstellar Studies have developed Project Lyra, a concept for a dedicated interstellar probe mission. The aim of Project Lyra is to catch up with an interstellar object like Oumuamua, or a future one, and conduct in-depth observations or even sample collection. The challenge is immense. Interstellar objects travel at tens of kilometers per second, far faster than any spacecraft we've launched to date. Project Lyra's proposed solution involves a complex trajectory using gravity assists and a solar orbit maneuver to achieve unprecedented speeds. In one scenario, a probe would swing by Jupiter to slow down, counterintuitively, and then make a close pass by the Sun. At its closest approach to the Sun, the probe would fire its engines to gain maximum speed boost, a technique that leverages the Sun's gravity for extra thrust. The result could be a probe traveling 70 kilometers per second or more, fast enough to eventually overtake Oumuamua. The mission design envisions launching by 2030 and intercepting Oumuamua by around 2048, after a decade-long journey. Another trajectory option skips the solar dive in favor of multiple planetary flybys, Venus, Earth, Jupiter, to gradually increase speed, arriving slightly later but with a more manageable approach speed. Either way, such a mission would be technologically challenging, requiring advanced propulsion, heat shields for the solar pass, and autonomous navigation to find a small object in deep space. However, none of the required technologies are fundamentally impossible with current knowledge. The main hurdles are cost and priority. Such an interstellar chase mission would be expensive and has not yet been officially approved by any space agency. Project Lyra remains a concept study, but it demonstrates that catching up to an interstellar interloper is technically feasible with a bold engineering approach. If humanity decides the scientific payoff is worth it, a mission like this could become reality in the coming decades. Future interstellar missions. Beyond Project Lyra, the encounter with Oumuamua has reinvigorated interest in interstellar travel technology. Concepts like Breakthrough Starshot, which proposes using light sails propelled by powerful lasers to reach nearby stars, could, in theory, be adapted to intercept interstellar objects in our solar system on short notice. In the nearer term, space agencies are also considering dedicated asteroid/comet interceptor missions that could be repurposed for interstellar targets. For example, NASA's Double Asteroid Redirection Test, DART, and ESA's Hera missions demonstrate our ability to target and study small bodies in deep space, techniques that could one day be applied to an interstellar visitor. The key lesson from Oumuamua is that we should always be ready. Interstellar objects might pass by at any time, and we need flexible mission architectures that can be redirected on relatively short notice. As one astronomer quipped, we need a space telescope on wheels, or in this case, a spacecraft on standby, to chase the next interstellar vagabond. Oumuamua will go down in history as a watershed moment in astronomy, the first confirmed interstellar object to grace our solar system. Its brief visit taught us that the space between the stars is not empty, it is crisscrossed by nomadic objects from other planetary systems. While we were fortunate to spot Oumuamua, we were also humbled by how little we could learn about it before it slipped away. The questions it left behind: what was it made of? Where did it come from? Why did it accelerate? Remind us of how much we have to discover about the wider universe. Importantly, Oumuamua has galvanized the scientific community to improve our preparedness. With new telescopes scanning the skies and mission concepts on the drawing board, we are far more ready today than we were in 2017 to capture the next interstellar visitor and unlock its secrets. In the end, whether Oumuamua was a chunk of an alien world or a bizarre natural oddity, it has expanded our cosmic perspective. It showed that interstellar travel is not just the stuff of science fiction, objects routinely journey between the stars, and one literally dropped in on us. As we continue to explore, there is every reason to expect more surprises. The next Oumuamua might arrive tomorrow or a decade from now, but whenever it comes, we will be watching closely. And if we're lucky, we just might send a probe to say hello. After all, in the vast ocean of space, even a tiny interstellar messenger can carry profound lessons, teaching us about other solar systems, the processes of planet formation, and perhaps, one day, even the possibility of life beyond Earth. Hey, thanks for watching. If you enjoyed this video, don't forget to give it a thumbs up. Share it with your friends, leave a comment down below, I'd love to hear your thoughts, and if you haven't already, hit that subscribe button and turn on notifications so you never miss an upload. Thanks for the support, and I'll see you in the next one.